Let's take a look now at example 1 and try to find the center of gravity of a plate of uniform density which occupies the indicated region here. Now, if I take a look at this region, I can notice that it looks a little bit intimidating. It's not really being communicated in a very simple way. But let's go ahead and see what we actually have and how we can interpret what we have here. Of course, we'll notice, as the problem suggests, that R here is some positive real number. Okay, so we'll see regions being communicated more and more like this in this course, as well as next semester in a Calculus 3 class. So it's important to start to become a bit familiar with what's going on here. So to first try to get a sense of what this region looks like, I should note that I'm working with some set notation. In this set that makes up the region is a bunch of points. And this should hopefully make a lot of sense, at least at first glance, because when I think about any region of space that exists within the xy plane, there are a bunch of points that make it up. In here, there are a bunch of individual points that together all construct this given region. So what we're collecting here in this region R is a bunch of points. But how do we determine the x and y coordinates for the points that are inside the region, on the edge of the region, and those that are going to be outside of the region? How do we go about doing that? Well, let's go ahead and actually take a look to see how we might be able to do that in this particular case. And we can start by taking a look at the restrictions on the value of x. So what we know is that there's some positive number r, and the values of x that are permissible, that are allowed to be a part of our region, range from negative r all the way up to positive r. So maybe this is negative 1 to 1, negative 2 to 2, negative a million to positive a million, who knows? And what we also see is that our y values are bounded as well. Notice here the smallest y value that we can use ever is the value of 0. So that means that I can kind of see here that I'm going to have a bottom edge to my region that's going to be right here on the x-axis between negative r and r. There's not going to be anything located at all down here in the bottom. Okay, I can see though that the upper bound on y depends on the value of r, but it also depends on the value of x. So let's go ahead here and just try to see what's going to happen. Let's suppose, for the sake of argument, that I was over here at this x coordinate right now, and I want to see maybe all of the y coordinates that could go along with this particular x coordinate. We know that the smallest y coordinate that's possible is 0, but what would be the biggest? If I was at the x value of negative r, what would happen if in place of x I put in negative r? Can you think about what you would end up with? How would this upper bound on y simplify? Well, in this case, you might see that it actually simplifies to 0. That is, if I plug in this negative r, I'm going to get r squared, and r squared minus r squared is 0. And so this would simplify down to y has to be in between 0 and 0. That is, y actually just is 0. So when x is this value, negative r, the only y coordinate I can ever have with that point is 0. Now, contrast that with what happens if I moved over to the x coordinate of 0. In this case, still the smallest y would be at 0, but what would the biggest possible value of y be if x was a 0? So again, if I plugged 0 in place of x. Well, in this case, I would note that I'm going to just get r squared minus 0. That's just r squared. And the square root of r squared should just be r, since r is already a positive number. So that would mean that I get up here. So I can start to see then that the region that I have is going to kind of contain this yellow point right there, and also all the points along this y-axis up to r and down towards 0. Now, we can continue to take a look and test individual points, but what might be helpful is to note that this right here represents an upper bound, and so I might be curious as to what shape this would look like if I kind of graphed the function y equals r squared minus x squared, where r is again just some positive number. Now, what you might be able to tell is that by simply squaring both sides and maybe adding over the value of x squared, I could see that I get an equation that's going to come out like this. And any idea what an equation like this might look like? You might guess, yeah, this is a circle. What I have here is actually the equation of a circle of radius r. And so what we have here is the top half of the circle as our particular region. And so we're interested in finding the center of mass, or the center of gravity, for this particular yellow region. Now, of course, with some practice and time, you'll get much, much better at kind of determining these regions from this notation. We won't use this a lot. I often won't ask this on things like exams just because it's a little more challenging, but every so often we'll do things like this in class. All right, well, now that we have our region established, where is that center of mass? Where is that balance point? And again, we should notice that this is going to be pretty easy to calculate using the formulas we established in the last video. We'll see that we have two integrals that we would need to calculate here, but we're also going to need to know A, the area of the region. So I'll start here by saying that we first find the area of the region. Now, there's a couple different ways we could do this. We could try to do this with calculus by saying I'm going to take this particular curve, which again was y equals the square root of r squared minus x squared, and we could attempt to integrate that from negative r to r to find the area of the region, just like you would in a Calc 1 class. However, what we could also do is to just note that since the region that we're working with this time is a nice geometric shape, it's just half of a circle, we could find this just by using geometry. So I'll write that down. Since we have a nice geometric shape, we will find the area using geometry. Okay, so let's see. The area of my region here would just be half of the area of a circle. And the area of a circle is pi, radius of the circle, squared. So I guess this is it, just 1/2 pi r squared. Or what I could also write as pi r squared divided by 2. All right, so now we could go ahead and move into calculating our x bar and our y bar. We'll just note that at the front of each of these integrals, I have to have 1 over the area, which would just be represented by the reciprocal of this fraction that we generated here. So let's go ahead and try to calculate this. To find our x bar, we would go ahead and compute, again, 1 over the area, which would be 2 over pi r squared, the reciprocal of this, times an integral from negative r to r. And then notice up here that I should have x times the function that I'm working with. So this would be x times an r squared minus an x squared dx. This is what I have to integrate. All right, now this is a little bit of a complicated looking integral. However, I could make this a lot easier by perhaps noticing that I can go back to my list of common integration techniques. That is, again, I have things like, is this a derivative rule that we learned in Calc 1? Is there any algebra I can do to make this simpler? Or do I need to use something like a U substitution to help me undo a chain rule? And what might be useful here is to see that we could use a U substitution. If we were to go ahead and let U be equal to r squared minus x squared, then du would be equal to negative 2x dx, which of course we don't quite have, but we could easily go ahead and just say that then a negative 1/2 du is equal to an x dx, right? Just divide both sides by negative 2. So now I can go ahead and I can see that my x dx can be replaced. And of course I can replace everything that I have underneath the radical. The only other thing that I'll also need to replace is our bounds. So let me go ahead and write that here. Say that our bounds become, let's see, I would take negative r, and I would plug that into my u formula to change it over. That's going to get me r squared minus a negative r squared, but that's just going to be r squared minus r squared, and so my new lower bound is going to be 0. when I replace my value of x with r itself, I'm actually going to end up with the exact same thing. So when I convert this integral over, I'll be able to see that x bar is going to then be equal to 2 over my pi r squared, and then I'd have an integral from 0 to 0. In place of my x dx, I can put in my negative 1/2 and my du, and then underneath my radical, I can just put in u. So if I try to simplify this up maybe just a little bit, make it look a little bit neater on the page, I should end up with an integral that looks like this. Remember here that u is my variable, not r. R is just some mystery number. But notice that this integral here is actually unbelievably simple to evaluate, because regardless of what's on the inside here, what's the integral, or the area, that I would imagine under a function like this from 0 to 0? Well, as you might recall, that's just going to result in 0. So I can automatically see then that wherever the center of gravity is, it exists somewhere along my x-axis, my y-axis, where the x-coordinate is 0. And if you think about it, that actually makes a lot of sense if you were intuitively trying to find the balance point for this region. It would have to be somewhere along this line. Okay, so let's go ahead and try to nail down exactly what y-coordinate we're going to be sitting at. We know that we already found the x-coordinate. To find y bar, we're going to have to go ahead and compute, again, 1 over the area, and then times an integral from negative r to r. And we'll have our 1/2 times our function, r squared minus x squared, being squared. Now actually, this is really convenient because this is going to make this integral very, very simple. That is, the fact that it's being squared right now, there the function is going to make this simple. So let's see, let's try to simplify some stuff up. Well, notice here that we have a 2 multiplied out front, and if we pull our 1/2 out to the front, that's going to simplify down. So we can write our integral now to look like the 1 up here, and we remove the 1/2 from the inside. When I square the quantity in there, I'm just going to be left with r squared minus x squared. Keep in mind right now, r represents a number, not a variable. So r is just some mystery number. Pretend r right now is the number 7. And x is the variable. So when I try to go ahead and integrate here, I'm going to end up with an r squared times an x. Notice that would be my antiderivative for the first part, minus a 1/3 x cubed. And I would need to evaluate that from negative r to r. Again, notice here I don't get something like a 1/3 r cubed because r is not the variable x. If this was, say, the number 7, then it's just, what's the antiderivative of 7 squared? Or what's the antiderivative then of 49? And the answer to that would just be 49x. It's just that same number multiplied by x. Now I have to evaluate it from a to b. And when I do this, I end up with a 1 over a pi r squared. And then I have, let's see, when I plug in positive r, I get an r cubed minus a 1/3 r cubed. And then when I plug in my negative r, notice I'm going to get a minus in r cubed. And then over here, I would ultimately end up with a plus 1/3 r cubed. And if I attempt to simplify this down a bit more, I can see that, well, here I have 1 r cubed, and here I have a 1/3 of an r cubed, and they're being subtracted. And so what I should end up with is 2/3 of an r cubed. I can also see that in my next set of parentheses here, I have a minus 1 r cubed plus a 1/3 of 1, and that should leave me with negative 2/3 r cubed. So if I have 2/3 of an r cubed and I minus another negative 2/3 of an r cubed, I should end up with a total of 4/3 of an r cubed. And if I put all of this together, I can see here that I'm going to have some r's that are going to be multiplied to the top of this fraction, some r's that are already on the bottom, and so I get some that are going to cancel out. And I'm going to have a 4r over a 3 pi. Now, if I take a look at this, this can seem like kind of a weird answer. That is, well, how do I know what this value is? How would I test to see if this is kind of a reasonable intuitive result? 4 times a mystery number over 3 pi? Where does that fall on here? Well, a good way to try to estimate this is to just quickly think, if I rewrote this here as 4 over 3 pi times an r, guess I don't need squiggly equal signs there, but if I wrote it like this, I could go ahead and think, well, wait, 4 over 3 pi. 3 pi is roughly just 3 times 3, so this is like roughly 4/9 of r. Notice that's like a little bit less than half of r. Whatever r is, this is like around a little bit less than half of that. And so I could see that this is about less than half of an r. And I can see that 1 r is all the way up here, so half of an r would be located right around here, and so our center of mass is going to be located a little bit lower than where half of r is. This here is our center of mass. And you can see that actually does make a lot of intuitive sense. So we can go ahead and see here that our center of mass can be expressed as the point 0, 4 times r over 3 pi. Now don't worry, in a lot of future examples, I'm hardly ever going to give you something here where we're just going to have kind of an abstract value of r where you have to do these sorts of approximations to get a sense of what's going on. But I wanted to do it here just so we could see that we could do this even despite not knowing necessarily all the values of pertaining to the region at hand. I'm going to ask you to go ahead and take a look at the next example and try to do this a little bit, or this one here, on your own. And of course, in the next video, I'll go ahead and actually cover the solution to that, and you can check that to see if the work that you did is actually correct.